avec Aurore, on ne se connaissait pas, mais on s'est connus par l'intermédiaire de Ludovic May, que j'ai beaucoup fréquenté, qui est un des personnages de la cybersécurité du côté de Rennes, alors qu'Aurore est à Sofia. Dans une équipe INRIA qui est encore en constitution, qui a un très joli nom, je laisserai dire le nom de son équipe. Voilà, je ne vais pas révéler le secret, la confidentialité. On est quand même dans un milieu cyber, donc ce n'est pas à moi de dévoiler tout. Et accrochez-vous parce que peut-être que vous ne verrez plus vos navigateurs et les extensions de la même manière que vous les voyez aujourd'hui, une fois que vous aurez écouté Aurore. Je ne sais pas si j'ai fait j'ai mis assez de pression. Aurore va nous parler en anglais. On est très content de t'avoir avec nous. Et donc, la façon dont on va fonctionner pour les questions, il y a plusieurs. Donc, Aurore m'a dit qu'il y a plusieurs moments dans la présentation où on peut s'arrêter et poser des questions. Il y a 3 ou 4 grands chapitres, j'imagine. Je n'ai pas compté, mais enfin, oui, c'est ça. Donc, si vous avez des questions urgentes, vous levez la main. Et si vous avez des questions moins urgentes, vous les mettez dans le chat. Et de toute façon, on a plusieurs moments où on s'arrêtera pour traiter les questions. Donc, merci encore. Je te passe la parole et on est très, très intéressé à avoir peur.
Merci beaucoup, Bertrand. Et maintenant, je vais passer en anglais.
Okay.
Donc, good afternoon from my side. My name is Aurore. I'm a tenured researcher at INRIA. And today, we are going to discuss how browser extensions can put the security and privacy of web users at risk. I'm originally from France. So I graduated from Telecom Nancy in 2017. Then I did my PhD at CISPA in Germany, followed by a very short postdoc. After that, I went to Stanford University, where I was a visiting assistant professor for 2 years. Then I went back to CISPA in Germany as a tenure-track faculty. And now, since December 2025, I'm back to France. I'm at INRIA in Sofia Antipolis. My research work broadly focuses on protecting the security and privacy of web users by using data science and software engineering techniques. During my PhD, I built systems to analyze, understand, and proactively detect malicious JavaScript code. More recently, my students and I have been building systems to detect dangerous browser extensions, which will be the focus of this presentation. And even more recently, we had several successful collaborations and published papers in other areas like internet measurements, machine learning, HCI, and also software engineering. So now for the remaining of this presentation, I'm going to focus on our research work on analyzing and detecting dangerous browser extensions. This presentation is structured in 5 main parts. I'm first going to present some generic background on browser extensions. Then I will define and explore what we call security noteworthy extensions. And then we will discuss how to detect vulnerable browser extensions, malicious browser extensions, and fingerprintable browser extensions. All these parts are pretty much independent. So yeah, if you doze off at some point, you can definitely come back and you can also ask questions between those parts. So let me start with some background. As you probably know, browser extensions are third-party programs that users can install to extend and customize their browser functionality. Most of us are using browser extensions all the time. For example, to add some ad blocking capabilities, perform grammar checks, provide some password management options, etc. There are currently over 270,000 Chrome extensions totaling roughly 3 billion active users, thereby also justifying a thorough security and privacy assessment of browser extensions. Every browser extension needs a manifest written in JSON called manifest.json, which gives some essential information about the extension. For example, the extension name, version, manifest version, but also the main components of the extension and the permissions of an extension. I'm going to go over the main components and the permissions in the next 2 slides. An extension is composed of 2 main components, a service worker, which used to be called background page, and content scripts. The core logic of the extension is implemented through a service worker. This is a JavaScript file which is running in the background of the browser, meaning independently of the lifetime of a window or of tab. It can handle events and has access to the privileged extension APIs specified in the manifest. So this is a privileged part of the extension. And then an extension can also inject content scripts into a web page. And similarly to the scripts already loaded by web pages, content scripts can use the standard DOM APIs to read and modify web page content. But contrary to service workers, content scripts, they have only restricted and limited access to the extension APIs. So again, really the core, the privileged part of the extension is in the service worker. If I illustrate that with a figure, so we have here an extension composed of the main components, content script and service worker. And these two components, they can communicate, they can interact by exchanging some messages. And they can also communicate outside of an extension. So for example, with a web page or with another browser extension. To use extension APIs, developers must declare those APIs in the manifest.json file. I'm giving you here a couple of examples. So for example, the storage API, as indicated by the name, is used to store or access data from the extension storage. The downloads API is used to be able to download some files. History API to access a user's browsing history. Bookmarks to access user bookmarks. Cookies, obviously, to access user cookies. Or top sites to access the most visited websites. And then there is also the host permission, which is also declared in the manifest.json file and represent web pages that an extension can access, meaning read or write, to do, for example, some cross-origin requests. If I give you now a short example of a manifest.json file, here the name of the extension is my extension. The manifest version of the extension is 3. Which extension APIs can the extension access? So the answer is downloads and history. From which domain can an extension fetch data? Here the answer is in the host permission, so example.com. And finally, on which websites is the content script injected? The content script is injected on any website, so all URLs, meaning HTTP, HTTPS, just every website. So that's it for the generic background on browser extension. And now we are going to move on to the more scary stuff and look into dangerous browser extensions. As I was saying at the beginning, the role of browser extensions is to provide some additional functionality to web users. But to do so, browser extensions need additional and elevated privileges compared to web pages. Think, for example, of an ad blocker. To operate, an ad blocker needs to read the content of a web page, including some sensitive information like credit card details, and rewrite the web page without the advertisement. An extension can also download some arbitrary files and access cross-domain data, while web pages cannot do that. This is blocked for security and privacy reasons. So my point here is that browser extensions can be and are an attractive target for attackers and can pose a significant threat to web users' security and privacy. How? Well, let's discuss 4 classes of dangerous browser extensions of interest to malicious actors to put the security and privacy of web users at risk. So the first category of dangerous extension are extensions containing malware. They are designed by malicious actors to harm victims. For example, those extensions propagate malware, steal users' credentials, or track users. A second category of dangerous extensions This time, they're designed by well-intentioned developers, but they contain some vulnerabilities, which can lead, for example, to sensitive user data exfiltration. Then a third category, there are extensions violating other policies from the Chrome Web Store. For example, the extension is describing functionality A, but in reality, it has functionality B. Or the extension is collecting some user data, but do not have a privacy policy. And finally, the fourth category of dangerous extensions are fingerprintable browser extensions. So those extensions can be detected by websites to build unique user profiles for tracking. I'm going to focus first on the top 3 categories of dangerous extensions, so containing malware, containing vulnerabilities, and violating other policies from the Chrome Web Store. And in our paper, we call those extensions security noteworthy. So the first question is probably, how can users install security noteworthy browser extensions? Like, could you accidentally install such a dangerous extension? Maybe because to install a security noteworthy extension, a user just has to go on the Chrome Web Store, which is the official browser extension gallery from Google, choose the extension they want to install, and probably assume that they're safe. But they're not. We have shown that the Chrome Web Store contained over 26,000 security noteworthy extensions between 2020 and 2023. This is surprising because, again, the Chrome Web Store is the official browser extension gallery from Google, and also because Google has this vetting process where extensions are analyzed to look for suspicious behaviors before they are published on the Chrome Web Store. So this vetting process could work a little bit better. My students and I, we have published a paper at Asia CCS, where in addition to what I just presented, we also found that 350 million users installed security noteworthy extensions between 2020 and 2023. These dangerous extensions, they can stay on the Chrome Web Store for years. And finally, we also uncovered that extensions are critically unmaintained, and so they cannot benefit from recent security and privacy improvements. Now, you may be wondering, how do we know that? So let me explain. We used a platform called Chrome Stats to collect browser extensions. Chrome Stats is a platform that collects some historical data since July 2020 for browser extensions that currently are or used to be in the Chrome Web Store. So we collected data for roughly the 250,000 Chrome extensions that have been on the Chrome Web Store anytime between 2020 and 2023 when we conducted this analysis. So doing that, we could collect 26,000 security noteworthy extensions, as mentioned before, including 10,000 extensions containing malware, 15,000 extensions violating other policies of the Chrome Web Store, and 184 vulnerable extensions. Now, you may be wondering, how do we know that those extensions are containing malware or violating some policies? So we know that because when Google is removing those extensions, they're not just removing them, they're also adding a label saying, okay, this extension was removed for containing malware. And when Chrome Stats is crawling the Chrome Web Store daily, they also collect this label, meaning that when we use Chrome Stats to collect some historical data, we could also collect the label and know that like 10,000 extensions were removed from the Chrome Web Store for containing malware. And again, the label is directly coming from Google. So we also assume that the label is reliable. If Google said it's malware, then we consider it's malware. And then we also have roughly 226,000 benign extensions. So I put benign in quote. Here, I just want to say they're not known to be malicious or dangerous, but there are probably some dangerous extension in the benign set. But if they're not known yet, we also can't know that either. And so using this data set, we did some comparative studies. We started with how long do dangerous extensions stay in the Chrome Web Store. So they stay in the Chrome Web Store between 380 days for malware and 1,248 days for vulnerable extensions on average, so between 1 year and 2 years and a half. Even more worrisome are some outliers. If you look at these malicious browser extensions over there, it stayed in the Chrome Web Store for 8 years and a half. And what is even more surprising is that this extension had not even been updated, so it was just there, just malicious for nearly a decade and undetected. So as I said before, security noteworthy extensions, they put the security and privacy of web users at risk for years. And right now, it's not super clear why such dangerous extensions that are not directly taken down and detected by Google's vetting system. Next, we also investigated how large the user base of dangerous extension is. The median is very low, with hardly over 100 users per extensions. But again, there are some outliers with very large user bases, so that on average, there are between 4,000 users and 27,000 users for dangerous extensions. In total, 346 million users installed at least one security noteworthy extensions between 2020 and 2023. Since these dangerous extensions, they stay in the Chrome Web Store for years, it is critical to improve their detection and notify impacted users, which is what my students and I are currently doing. Our paper received a significant media coverage. After our paper appeared, Google also published a statement saying not to worry, that only 1% of all installs from the Chrome Web Store are containing malware. Now, I don't know if you remember what I said at the beginning. There are currently 270,000 browser extensions on the Chrome Web Store. So 1% actually represents a very large portion of extensions. So that's it for security noteworthy extensions. And before moving to vulnerable extensions, do you have any questions?
Moi, j'ai commencé. On peut les faire en français?
Pas de problème.
Parce que, en fait, on parle d'extension du Chrome Web Store, donc, mais c'est le seul web store c'est pas le seul web store qui contient des extensions. Est-ce que pour d'autres navigateurs, c'est un peu la même chose? Et puis je me demandais aussi, par exemple, Comet, c'est un browser qui est bâti sur Chrome, c'est le browser de Perplexity qui contient un assistant IA, mais en plus, il est bâti, on voit très bien qu'il est bâti sur Chrome, donc ça s'applique aussi à tous ces navigateurs-là.
S'ils ont des extensions, oui. Et donc, par exemple, Firefox ou Edge, ils ont aussi un système d'extension, mais ils ont beaucoup moins d'extensions que Google. Donc, on ne va pas avoir des chiffres aussi fous avec 26 000 extensions dangereuses. Mais bon, voilà, les stores, ils sont beaucoup plus petits, mais il y a aussi des extensions dangereuses dans les autres stores.
Et idem, j'imagine aussi pour les mobiles. Alors, les mobiles, il y en a plein qui utilisent Chrome aussi, mais il y a également d'autres navigateurs sur les mobiles, donc c'est valable aussi pour toutes les plateformes, finalement.
Alors, je ne sais pas s'il y a des extensions sur mobile, j'ai un doute. Je sais pendant un moment, il n'y en avait pas. Maintenant, je ne sais pas si c'est le cas ou pas. Mais voilà, tous les navigateurs qui ont des extensions, ils sont concernés par ça.
Tiens, je vais regarder sur mon mobile pendant qu'on en parle. Est-ce qu'il y a d'autres questions? Est-ce qu'il y a d'autres questions? Une fois? Deux fois? 2 fois et demi? Allez, on continue. Merci beaucoup, Aurore. On continue.
OK, on continue. So now moving on to detecting vulnerable browser extensions. Vulnerable extensions, they are challenging to detect because if it were not for the vulnerability, they would actually be benign. So they really look like a benign extension. And now you may be wondering, what is a vulnerable extension? How does it look like? So let me explain with an example. Let's assume you receive a phishing email. You click on the link and you end up visiting a malicious web page. This is already bad on its own, but this is much worse if you visit a malicious web page while having a vulnerable browser extension installed. Why? because the malicious web page can communicate with the vulnerable extension and can tell the vulnerable extension to do things that the web page could not do on its own. For example, for security and privacy reasons, Facebook.com cannot collect the cookies from your banking website, but a browser extension can collect all users' cookies on any web pages. So the malicious web page just needs to ask the vulnerable extension to get all the users' cookies. Meaning that this communication process between the malicious web page and the vulnerable extension is a way for the malicious web page to exploit the elevated privileges of the browser extension and to do things that a web page could not traditionally do, like exfiltrating sensitive user data, cookies or browsing history, triggering some arbitrary downloads without user consent, or even the user noticing that something is being downloaded on their computer, and potentially stealing data from other websites. These types of vulnerabilities, they were known, but existing analyses were mostly manual, and there was no large-scale automated solution to detect vulnerable browser extensions. Which is why, to mitigate this, in 2021, we proposed our system DoubleCross to automatically detect vulnerable browser extensions. I'm going to explain at a very high level how DoubleCross operates by using an example. We have here a vulnerable extension with two components, content script and service worker. And here is the malicious web page that the user is visiting. At a high level, DoubleCross models the source code of each extension component with a graph, with an abstract syntax tree containing some control and data flow information. Then it models the communication both within an extension and also outside of an extension, so between the malicious web page, meaning the attacker, and the browser extension. And finally, DoubleCross needs to figure out if there is a path for the malicious web page to access the privileged functionality of the browser extension, like the cookie API, for example. So basically what we are doing here is some static analysis of JavaScript with some taint tracking. And I'm not going to go in any more technical details, but I'm going to take an example instead to illustrate how DoubleCross can detect vulnerabilities. So here we have a browser extension with just one component, a content script. And the content script is listening to messages coming from web pages. The received message is in the event variable and is going into eval. So eval is a JavaScript function that enables to execute arbitrary pieces of code. So here we have an arbitrary code execution vulnerability in the content script, which DoubleCross can detect. So this means that an attacker, they can just send a message to the extension, and the message of the attacker is directly going to be executed inside the extension. So if I give you an example of a message, so if an attacker is sending a post message containing alert of 1 to the extension, then on the user's browser, there will be a pop-up indicating 1, which is going to appear, which, okay, it's not super malicious, but my point here is that the attacker can just send whatever they want to the extension, for example, steal all users' cookies, and then the browser extension is going to execute that directly on the user's browser. Let's have a look now at one real existing vulnerable extension that DoubleCross detected. This extension is totaling 4,000 users, and it can be exploited by any websites to execute arbitrary code in the extension context. So how does it work? Well, the content script can receive messages from any websites, and then the content script is just forwarding all messages to the background page, which is the privileged part of the extension. And here, the message content is directly executed in the tabs.execute script API, which is also executing code. So here, the message sent by the malicious web page is directly executed within the extension. So this example is highlighting the danger of trusting input data provided by like a web page by an attacker. And if I try to give you an analogy, if you found a USB stick on the floor, you wouldn't plug the USB stick coming from, a random person directly on your computer. You don't know what is on the USB stick. It can be dangerous. Here, it's exactly the same thing. I mean, you receive a message, like the extension receives a message coming from an external source that it doesn't know. So it should not randomly execute the message. All right. So we evaluated double cross on 155,000 Chrome extensions, which was like the number of extensions in 2021 when we did this analysis. Overall, it detected 184 vulnerable Chrome extensions impacting 3 million users. Our tool has a high precision, so we could manually verify that 89% of the extensions flagged as vulnerable by double cross, they were really vulnerable, and we could exploit them locally on our own machines. And double cross also has a high recall. So there is another paper from Sommet published at S&P 2019, which identified some vulnerable extensions. We used his data set and we evaluated double cross on his data set of known vulnerable extensions, and we could identify 93% of known vulnerabilities. Our prototype is open source, and it can help not only well-intentioned developers check for vulnerabilities in their extensions, but it can also be used to analyze any applications written in JavaScript. For example, double cross is already extensively used to analyze mini apps and even more recently, VS Code extensions. Now, how can we mitigate that? Because so far I have more or less presented you what, not to do, what developers should not do. So what should developers do instead? So I put here a very short list of what developers should do, starting with migrating their extension to Manifest v3. But I mean, now all the extensions are Manifest v3 anyway, so, it should already be done. And then it's mostly awareness. Like, a developer should know that if their extension can communicate with other web pages, with other extensions, it can be dangerous. And they should only allow the communication with some very specified extensions or web pages. So, for example, you would not leave the keys to your house to a stranger you just meet on the street. You would maybe leave the key to your house to some good friends or family. So here it's exactly the same, just, don't share with everyone. Then obviously limit code execution by sanitizing messages. So that's what I was saying with the USB stick. You just don't plug a USB stick on your computer, like if you don't know what's inside. So here it's the same thing. You don't execute messages coming from an unknown source. And finally, obviously, double cross can also provide a feedback channel for developers, and developers could run the tool to see if there are any vulnerabilities in their extensions, or Google could also use the tool for that. And now you may be wondering, what should you do as a user? And here it's harder. Like I would say, be careful. Be careful which extensions you're installing, and maybe think about, do you trust those extensions or not, because they have access to a lot of sensitive information about you, and also they have like privileged access inside your web browser. And awareness, be aware that extensions can be dangerous. And so again, carefully think about which extension you install and why you install them. All right, so that's for vulnerable extensions. So before moving on to detecting malicious browser extensions, do you have any questions?
Alors, moi j'en ai une ou deux, mais je vais quand même laisser les autres en priorité. Allez-y. Bon, bah vous êtes toujours tranquille. En fait, de ce que j'ai compris, le danger passe par la fonction eval de JavaScript. En fait, je ne suis pas expert de JavaScript, mais dans d'autres langages, j'ai utilisé des choses comme ça, des fonctions eval. C'est extrêmement puissant, mais c'est vrai que c'est aussi très risqué. Donc, est-ce qu'il y aurait moyen dans un navigateur, ou je ne sais pas de quelle manière, d'inhiber la fonction eval pour être tranquille.
C'est
Ah,
une
c'est
bonne
peut-être...
question. Oui. Alors pour eval, oui. Donc l'étude là, elle a été faite en 2021, mais maintenant avec le nouveau manifeste V3, eval, c'est plus possible d'exécuter du code qui vient pas de l'extension. C'est pas possible d'exécuter du code qui vient de l'extérieur avec eval. Enfin, c'est plus possible, c'est bloqué. Donc, du coup, pour répondre à la question, voilà. Donc maintenant, ce problème-là est résolu. Mais
Ok,
après, eval, c'est juste un exemple que j'ai pris.
ok,
Voilà, c'est possible d'exécuter du code, mais après, il y a d'autres soucis. Par exemple, ben, les cookies peuvent aussi être exfiltrés, mais là, ça n'a pas de rapport avec eval. C'est juste si l'extension, ben, elle pense envoyer les cookies à, je sais pas, une page web en particulier, mais en fait, elle l'envoie à toutes les pages web qui sont en train d'écouter les messages de l'extension. Donc, oui, on va dire qu'eval aujourd'hui, c'est résolu, mais il y a encore beaucoup d'autres
d'accord.
enfin, de vulnérabilités de sécurité.
Milad, je te laisse poser la question.
Oui, merci Bertrand. Oui, du coup, la question c'était que est-ce que DoubleX que vous avez développé, est-ce que du coup, ça sert que pour les développeurs ou aussi pour les usagers normaux ou les utilisateurs qui
Bah,
peuvent
même
installer?
Oui, c'est une bonne question aussi. Un utilisateur pourrait aussi l'utiliser, donc c'est sur GitHub, mais après, c'est pas. Enfin voilà, disons que c'est un utilisateur qui sait quand même un petit peu ben, ce qu'il fait parce qu'il faut, il faut enfin, cloner le projet sur GitHub et puis après, il faut télécharger l'extension, il faut l'analyser comme ça. C'est vrai qu'à un moment, j'aimerais bien avoir plutôt un site web où du coup n'importe quel utilisateur lambda pourrait juste cliquer sur un bouton en disant est-ce que les extensions que j'ai installées sont vulnérables ou pas. Mais ça, c'est quelque chose que j'ai malheureusement pas eu le temps de faire encore.
Merci.
Est-ce qu'il y a d'autres questions? Juste moi, pour revenir sur la discussion d'avant, donc j'ai demandé à Perplexity si on pouvait mettre des extensions sur les mobiles. En fait, il me dit pas sur Chrome pour Android, mais il me dit, mais finalement, il y a d'autres navigateurs basés sur Chromium. Il me suggère Kiwi Browser ou Yandex Browser. Alors Yandex Browser, ça doit être russe, donc de toute façon, je me méfie. Kiwi Browser, je ne sais pas d'où ça vient, mais il me dit finalement Kiwi Browser, lui, c'est le même genre et il y a une possibilité de mettre des extensions dedans, depuis le Chrome Web Store.
D'accord, ok. Bon, alors ça, je ne savais pas, mais du coup, potentiellement, il y a les mêmes soucis sur mobile. Et puis en plus, souvent, on va dire que le desktop, il est un petit peu mieux sécurisé. Il y a plus de recherches que sur mobile, donc je serais encore plus inquiète d'utiliser des extensions sur mobile, personnellement.
Est-ce que parmi nous tous, là, il y a quelqu'un qui utilise ou qui connaît Kiwi Browser? Moi, je ne connaissais pas. Non, bon. Ok, on peut continuer. Je ne vois pas d'autres questions en ligne, donc on continue. Merci, merci.
Ok, ça marche. Donc, moving back to detecting malicious extensions. And so again, this is like a separate part of the presentation. So if I lost you at any points before, you can come back now. So to detect malicious browser extensions, we designed a machine learning-based pipeline, which appeared at TWeb 2026, so very recent work, and which is going to be presented next week Friday, sorry, at the web conference remotely. To develop a machine learning-based pipeline, we need three things. We need a labeled data set of benign and malicious browser extensions. We need some features to extract, and we also need classifiers, detectors to train. We trained our detectors on 80% of our dataset, and we made some predictions. We evaluated our detectors on the remaining 20%. We collected benign and malicious extensions from ChromeStats. So ChromeStats is a platform I mentioned before, which is collecting browser extension data every day from the Chrome Web Store about extensions that are in the Chrome Web Store and used to be on the Chrome Web Store. And we know those 7,000 extensions are malicious because Google removed those extensions for being malicious. And then we have over 60,000 benign extensions. So I also put some quote on benign because they may contain some malicious extensions, but they're not known to be malicious as of now. And also we focus on extensions last updated in 2022 for the benign set. We did this analysis in 2023. Maybe I should have said that. So that the extensions, they have been on the Chrome Web Store already for at least a year. And so we assumed that, if they were malicious, maybe they would have been detected by them. So here it's totally best effort. And then we extracted some features from those extensions. we extracted features from the source code of the extension. So using one of my tools, which is building an abstract syntax tree from JavaScript code and then extracting some syntactic units. And we also considered metadata. So like, what are metadata? For example, extension permissions or number of users or extension ratings or extension description. So basically anything about the extension that is not related to the code. And using those features, we trained 3 classifiers. The first one is based on the source code. The second one is based on the metadata features. And the third one is a combination using both the source code and the metadata features. All our classifiers performed well on our testing set, with the classifier performing the best being the combined classifier with an accuracy of almost over 98%, true negative rate of almost 99%, and true positive rate over 95%. So we were very happy with the detection performance of our detectors. And we thought, okay, it's working well, the performance are good. So now let's use our detectors in the real world. So in other words, let's take the 30,000 extensions on the Chrome Web Store, last updated in 2023 and later, so that we have not considered them before. And let's check how many of those extensions are malicious. So we classified those extensions with our combined classifier, which performs the best. And surprisingly, almost 3,000 extensions were classified as malicious, which, this is a lot. It's 10% of the set of extensions we classified. And, we did not believe for 1 second that there could be so many malicious extensions on the Chrome Web Store, like 10% of the Chrome Web Store being malicious. I mean, this is really not possible. So we were wondering what is happening, why are so many extensions flagged as malicious when our detectors were performing so well on our testing set? Obviously, we cannot manually review these 3,000 extensions. So we looked for some approaches to decrease the number of extensions flagged as malicious so that we could look into them and understand a bit better what is going on. So we decided to create an ensemble, so to use the metadata classifier, the source code classifier, and the combined classifier together. And if all of them are saying that a given extension is malicious, then we assume that it's more likely that the extension is actually malicious. Unfortunately, still over 1,000 extensions are flagged as malicious, which is still too much for us to manually review those. So what we did instead, we first checked if Google had identified any of those extensions as malicious in the time we needed to do the experiment, and they had. So 28 of those extensions were really malicious, impacting 2 million users. But we still had, 1,000 extensions to manually review, which is not possible. And so instead, we decided to do some clustering. So to cluster extension together when they had like a similar source code, and to manually review some extensions per cluster. Doing that, we could identify 40 malicious extensions impacting 11 million users. So overall, we identified 68 malicious extensions impacting 13 million users, which on the one hand is, is a lot because there are these dangerous extensions that were on the Chrome Web Store impacting users. But at the same time, out of the roughly 200 extensions we manually reviewed, there is like a huge false positive rate. But anyway, we reported the 40 unknown malicious extensions directly to Google. And unfortunately, we did not receive any response. So already in May 2024, when we disclosed them. As of September 2025, and actually as of today, 17 out of the 40 malicious extensions were taken down, which on the one hand is good, but on the other hand, it means that there are still 23 known malicious extensions that are on the Chrome Web Store today. But this is only one part of the concerns. Like the other part of, or my concern is, what is going on? Like our detectors were performing really well. We had an accuracy over 98% in our lab setting. And now when we try to deploy the detectors in the real world, it flags over 1,000 extensions as malicious out of 30,000. And we could verify that only 68% of those were really malicious. So, it doesn't seem like our detector is working so well. So we were wondering what is going on? What is happening here? Like, why does it work in the lab setting, but not in the real world anymore? And the answer is concept drift. So what is concept drift? The thing is extensions, they're evolving and changing over time. This is natural, or because there are new APIs, because there is this new manifest version, but the problem is this evolution makes it hard for supervised machine learning tools to keep up the great performance over long periods of time, which is why in the real world it was not working so well. And now if you're curious about how to evaluate concept drift or why our extensions impacted by concept drift, these are very good questions, which we explain and quantify directly in the paper. So what should you take away, from this maybe failed experiment? Well, machine learning evaluations can be misleading. A detector performing well in a lab setting is not a guarantee of practical applicability in the real world. And then obviously the detectors need to be retrained regularly. And we investigated a little bit active learning as a mitigation to concept drift, where basically when we retrain the detector, we give some new extension to the detector to retrain the detector on those extensions where the classifier was the most uncertain about their classification. So, it helps the detector get a little bit better. But this is exploratory for now. All right, so that was it for detecting malicious extensions. And now, before moving to fingerprinting, to detecting fingerprintable browser extensions, do you have any questions?
Moi, je trouve... oui, alors il y a quelqu'un qui lève la main. Je vais laisser Faisal commencer.
Merci Bertrand, merci beaucoup. Oui, une petite question sur le drift detection pour les aspects machine learning. Enfin, si je peux me permettre en français, sinon je peux switch about machine learning and drift detection. Could you mention some pilot machine learning approaches in this context?
What do you mean with pilot?
Like quite enough used machine learning approaches to detect this conception drift. Are they typically probabilistic approaches? Are they deep learning, or if you can comment about that? Yeah.
So yeah, maybe if I come back to this slide. So what we did was we trained our classifier. So we use random forest, like the machine learning algorithm. And we trained our classifier, for example, in January. So all extensions last updated in January or before, they were used to train the detector. And then we evaluated the detector on extensions last updated in February. And then on extensions last updated in March, April, etc. And this is the experiment from the paper, and we can really see the accuracy decreasing over time. So there is, like here in this experiment, there was no retraining, and we could really see that the detector is it's just getting worse and worse over time. And that's through this sort of experiment that we validated the concept drift hypothesis.
Okay, thank you very much. So I see it is a random forest. Thank you.
You're welcome.
Bon, moi, je vais continuer en français. D'abord, je trouve assez intéressant le fait qu'on soit on part sur un problème de cybersécurité, et puis mine de rien, on arrive sur la question de confiance dans l'intelligence artificielle assez rapidement. Donc ça prouve que c'est vraiment un gros sujet qui est partout, même dans des endroits où on ne l'attendait pas tellement finalement. Non, la question que j'avais, c'est sur l'ensemble, parce que le premier détecteur code, le deuxième metadata, et le troisième, il fait code plus metadata. Donc quand on met les trois ensemble, je me dis, y a de la redondance là, parce que
Oui.
le troisième doit, enfin, l'ensemble doit pas faire tellement mieux que celui qui prend déjà la somme des deux autres, quoi. Si...
Oui, non, je suis complètement d'accord. Bon, peut-être pour le contexte, le projet là, ça venait d'un mémoire de licence. Et donc, il avait évalué ça dans son mémoire. Et puis, nous, voilà, quand on essaie d'en faire un papier, on s'est dit, bon, 3000 extensions qui sont indiquées comme étant malveillantes, qu'est-ce qu'on peut faire? Donc, on s'est dit, bon, on n'a pas grand-chose à perdre en essayant de combiner les 3 détecteurs pour regarder si ça permet de diminuer un petit peu. Puis, ça a quand même diminué d'un facteur 3. Et je suis assez d'accord, c'est un petit peu surprenant parce qu'il n'y a pas de nouvelles features finalement, comme on a déjà les features qui sont combinées avec le Combine Classifier.
Bah oui.
Mais après, comme c'est Random Forest, ça veut aussi dire, la façon dont l'algorithme fonctionne, il ne considère pas non plus toutes les features à chaque, on va dire à chaque nœud, à chaque split. Donc c'est possible aussi que ce ne soit pas tout à fait les mêmes features qui soient considérées dans les 3 détecteurs quand on les combine.
D'accord.
Mais bon, là, ça devient un petit peu trop machine learning pour moi.
Oui, ok. Est-ce qu'il y a d'autres questions? Non, on peut passer à fingerprintable extensions.
Okay, so yeah, the last part on detecting fingerprintable extensions. So browser extension fingerprinting originates from the fact that browser extensions can interact with web pages. And here in this presentation, in our paper, we focus on 3 different ways for these interactions between browser extensions and web pages, but there are more. So the first one is post messages. So as for vulnerable extensions, so extension can send post messages to web pages. If I give you an example, so we have a user visiting the webpage example.com while having a browser extension installed. Now, the browser extension can send messages to the website. And if a specific extension is always sending like a very specific and unique message to any web pages, then a random web page can know that if it receives this message, then it means that the user must have this specific extension installed. All right, a second way to interact with web pages is by storing data on the client side using different storage APIs like cookies or local or session storage. If I take my example again, a user visiting example.com while having a browser extension installed, the browser extension can store things on the client side, which is shared with the web page. This means that if the browser extension, again, is storing like a very unique message or object in the client side, the web page can query the client side storage to see what the extension has stored. And as before, if we have this extension, which is always storing this specific message, and only this extension is storing this message, then the web page can know, oh, the user must have this specific extension installed. And then the third vector we considered, extensions, they often inject JavaScript code directly into the visited web page. For example, browser extension scripts may register global variables, which the web page is directly able to observe or even to invoke, and also global APIs and properties, which a web page can also observe. So these 3 vectors here, they leave traces. So they leave observable side effects that can be seen by a malicious web page. Now, this is a little bit technical, but for the first vector, if a web page has a message listener, so if a web page is listening to any messages sent by an extension, then the web page can collect those messages and have a sort of database where, it's stored, okay, this extension is always sending this message. So if I receive this message, then necessarily the user has this extension installed. For the storage APIs, web pages can probe for items in the client-side storage. For example, every 500 milliseconds, check what is in the client-side storage to also observe which extension is storing data in the client-side storage and detect which extension a user has installed. And finally, for the third vector, a web page can, obviously directly access global variables. And for global APIs or properties, a web page can overwrite their native definition to be able to first, provide a log saying, hey, I'm being executed before the API is doing whatever the API is supposed to do. So yeah, I don't know, this is very technical, but the question is, why is this bad? Because I keep telling you, okay, like there are several ways where a malicious web page can know which extension a user has installed. But why is this bad? Like, why do you care if a web page can know which extension is installed on your browser? Well, I would say there's 3 reasons why this is bad. First, extensions can be detected by websites to build unique user profiles for tracking. And the more extension you have installed and the more unique your profile, your pattern is becoming, and so the easier it is for a web page to track you. A second reason, well, if a web page can know which extension you have installed, if you have a vulnerable extension installed, an attacker can know, and an attacker can abuse that. And finally, being able to detect the extensions the user installed is also bad because it leaks some personal information about the user. For example, geolocation or social or personal interests, some medical issues, if you have an extension installed about, I don't know, your diabetes or something like that, etc. So now we were wondering how many extensions in the Chrome Web Store can be uniquely fingerprinted by the 3 vectors I presented. And to answer this question, we propose our tool called Radar, which was published in 2024. With Radar, we analyzed 38,000 Chrome extensions in 2024, and we only analyzed those extensions from the Chrome Web Store that could interact with any web pages. So for example, if an extension could only interact with example.com, then we did not analyze it further. Still, we uncovered over 2,700 fingerprintable Chrome extensions, which again is a lower bound since we excluded those extensions which do not interact with any websites. And those fingerprintable extensions, they impact 169 million users. We notified the roughly 2,000 developers who had published fingerprintable browser extensions, so explaining why the extension is fingerprintable, what it means, why it is bad, etc. And unfortunately, only 30 developers replied, and of those, only 16 positively acknowledged our findings. But the problem is, they also said they heavily rely on the fingerprinting vectors, for example, injecting script or storing some data directly for the functionality of their extension. So this is very hard to fix and to prevent the fingerprintability of browser extensions. Finally, our tool Radar is also available online and can be used as before, both by users or developers to check for the fingerprintability of their extension. And now let me briefly sum up what I presented. So browser extensions are popular, everybody's using extensions, but extension can be dangerous. Which is why we have proposed our system Double Cross to detect vulnerable browser extensions. We also discussed challenges related to the detection of malicious extensions in the real world. And finally, we discussed how to detect fingerprintable browser extensions. That's it from my side. I'm happy to take questions if you have any remaining questions.
Merci beaucoup, Aurore. C'était très, très clair et très intéressant. En fait, est-ce qu'il y a moyen de prévenir sur quelles sont ces extensions que vous jugez dangereuses dans le projet? Est-ce que, par exemple, tu aurais pu envoyer la liste des extensions dangereuses à l'ANSSI pour que l'ANSSI prenne des mesures de prévention?
C'est vraiment une bonne question, je ne sais pas. Bon, alors, bon, les projets là, ils ont été faits quand j'étais en Allemagne, donc ça n'aurait pas été l'ANSSI, mais l'équivalent allemand. Ce qu'on a fait, c'est qu'on a contacté soit Google, soit les développeurs. Donc, on a quand même reporté ça aux autorités qu'on pensait compétentes. Mais en pratique, il ne s'est pas passé grand-chose. Google, on n'a pas de réponse. On leur reporte régulièrement des extensions dangereuses, on n'a pas de réponse. Et c'est un peu random. Des fois, elles sont supprimées, des fois, elles ne sont pas. La moitié supprimée, l'autre moitié ne l'est pas. Et après, pour les extensions fingerprintable ou vulnérables, c'est plus de la responsabilité des développeurs à ce moment-là, parce qu'on ne veut pas forcément que Google enlève les extensions du Chrome Web Store. Enfin, ici, il y a moyen, on va dire, de réparer ça. Il n'y a pas de mauvaise intention derrière ça. Donc, c'est vrai qu'on a toujours interagi directement avec les développeurs, mais ça ne marche pas beaucoup. Mais du coup, c'est une idée intéressante d'essayer de voir s'il y a une autorité compétente supérieure, on va dire, ou qui
Ben, en
pourrait peut-être faire
France,
plus
ouais,
de
en
choses.
France, c'est l'ANSSI qui pourrait faire ça.
Mais c'est bon à savoir ça, merci.
Euh, et concrètement, par exemple, quand je veux lire un journal sur une page web et que le journal me dit enlever adblock, c'est l'option 2, c'est que l'extension a une signature dans un fichier qui est reconnu par le journal, en fait, c'est ça?
Voilà, c'est quelque chose comme ça. C'est pas forcément les vecteurs que moi j'ai présentés, mais la page web est capable de détecter, oh, il y a un adblocker ou voir enfin, si c'est adblock. Et c'est exactement ça.
D'accord. À votre tour, quand même, dernière chance avant qu'on finisse ce séminaire, que j'ai trouvé absolument d'abord très très clair. Vraiment, je trouve que c'est sans doute un peu la même présentation que tu vas faire la semaine prochaine
Euh,
à la webconférence.
oui, bah, du coup, la semaine prochaine, ce sera juste sur les extensions malveillantes, mais c'est
Oui.
ça.
Pas de questions? C'était trop clair. Bon, merci beaucoup, Aurore. On ne regardera plus les extensions de la même manière. Je m'y
Désolée.
attendais un tout petit peu déjà. J'avais déjà eu une présentation sur le fait qu'on pouvait être identifié par la composition de son browser avec les différentes les métadonnées et que ça nous identifiait de manière unique assez facilement. Et là, ça en rajoute un petit peu. Voilà, donc vous pouvez remercier Aurore et bonne fin d'après-midi à tout le monde.